So we're going to start looking at the review multiple choice items from the Princeton Review. So let's look at number 1. Why does calcium fluoride have a higher melting point than NH3? And when I look at these two, I would definitely expect this to have a higher melting point. And the reason is, this is an ionic substance. It forms a lattice, like I've kind of drawn up here, where the calcium and fluoride ions are together in these larger groups. And they have very strong lattice energy. NH3 is a isolated covalent compound, and they interact through intermolecular forces. And in this case, I think it's very likely to be a hydrogen bond between this lone pair and that hydrogen. And while hydrogen bonds are very strong, they're not flat out positive and negative charges. These really strong Coulombic attractions are really what's going to make this very difficult to melt, in other words, to break up. You got to remember, intermolecular forces are a little bit weaker than that. So keeping that in mind, let's look through the answer choices they give us. By the way, right away, let's get down to, I'm pretty sure the answer is going to be D. And D is not a very satisfactory answer because it's poorly written, but I think it's the best of the choices. So calcium fluoride is an ionic substance, that's true, and it requires lots of energy to break up an ionic lattice. It's a generalization, but it's certainly better than the other answers in here. If we look at A, calcium fluoride is more massive, as in heavier, and thus has a stronger London dispersion forces. Well, London dispersion forces don't have a big role in this sort of lattice. All compounds, it's true, do have London dispersion forces, but they're so weak compared to the lattice energy that would be exhibited there. So I don't think A is going to be the answer. B, calcium fluoride exhibits network covalent bonding. We actually don't talk a lot about network covalent bonding. Obviously, network covalent bonding has to involve covalent compounds, and calcium fluoride is an ionic compound, so that just doesn't seem like that's going to be the right answer either. Calcium fluoride is smaller and exhibits greater Coulombic attractive forces. Calcium fluoride does exhibit greater Coulombic attractive forces because it actually has positive and negative charges. Down here in the ammonia, remember we have these bond dipoles. Actually, I think nitrogen is going to be more electronegative. So we are going to have these partially negative and partially positive, and so there's going to be really weak Coulombic attractions. But it has nothing to do with the size of calcium fluoride. That might be a better situation. C might be a better situation if you were like comparing calcium fluoride to, say, I don't know, magnesium fluoride, where you had two identical ionic compounds and the size of these ions. Remember, the smaller one would have much stronger Coulombic attractions. So C doesn't seem like they're talking about the case that we're looking at here. Alright, so question 2. Which of the following pairs of elements is most likely to create an interstitial alloy? So before we look at these choices, we probably need to remind ourselves what an interstitial alloy is. Remember, that's the one where the atom that is the solute, the one that's impure, fits in the middle. And you see I drew over here, I drew a bunch of atoms, and the impurity atom, the solute atom, in an interstitial alloy fits in the little space between the other atoms. So it doesn't really disrupt the other atoms because it's small enough to fit in there. A spatial alloy, it would be a situation where you have atoms that are roughly the same size. Like, let's say that we had a solute atom that was trying to fit in here, and it was roughly the same size as the others. Well, it no longer can fit in the middle here, so it would have to actually replace one of these others. So that's a spatial alloy. So since we're looking at an interstitial alloy, like up here, it's definitely going to have to be the thing that the impurity, the solute, is going to have to be a lot smaller than the other atoms. So we're looking for two that are the biggest difference in size. So if we look at titanium and copper, there's titanium and copper. That's one choice. Look at aluminum and lead. There's aluminum and lead. And I think you can see right away, you remember that since francium is the biggest element on the periodic table and helium is the smallest, they get smaller as they go up and to the right, that there's going to be a huge difference in size between aluminum and lead. It's going to be a little bit of a difference in size between titanium and copper, but they're in the same row. They both have 4 rings of electrons. Not very different. So I think B is going to turn out to be the correct answer, because if you look through the others, let's see, where's silver and tin? Here's tin, and silver's right there. They're so close together. And then lastly, magnesium and calcium. Magnesium, calcium, they're so close together. I think that B is going to be the correct answer. Okay, number 3. Which of the following molecules would exhibit the strongest dipole moment? And so what they're saying there is, remember, dipole moment, essentially what that means is which of these is the most polar. That's what strong dipole moment means. So it's probably a good idea as soon as you see that, cross it out and write most polar. It's really helpful if you remember some of the structures of these, because then you don't have to draw them all out. But you remember, to determine if a molecule is polar or not, you got to draw out the Lewis structure, which means you got to count up the valence electrons. So if I was going to count up the valence electrons for CH4, well, the carbon would give me 4. Let's see, 1, 2, 3, 4. Each hydrogen would give me 1 each as I count across. So 4 plus the 4 from the hydrogens gives me 8 valence electrons. Put the carbon in the middle, spread the others out like this, and you notice we've used 2 in each bond already. We've already used 8, and it's okay because you remember hydrogen cannot have dots on the outside. We should never have any dots around the hydrogen out here at all. And you remember the other thing that's important to notice is Lewis structures. If you just draw them, that doesn't necessarily show you their shape, and we have to know their shape. And there's 1, 2, 3, 4 directions coming off of it. That means it's going to look most like tetrahedral. So it should really look like the carbon in the middle, the hydrogens sort of in that tripod shape that we've come to know. And you'll notice there's no lone pairs here, and tetrahedral is a symmetrical shape. So all of the dipoles cancel and there will be no net dipole moment. So definitely A is not going to be the correct answer. If you draw the others out, what you're going to notice is that BCl3 ends up looking like this with lone pairs like that. If you add up the valence electrons, do the whole thing, you have to draw out the whole Lewis structure. There's no way around it. Now I'm skipping the adding up the valence electrons, but you need to do that. You notice boron does not have a lone pair on it at the end after you spread them around the outside first, right? And then you go to the inside and you have none left. But that's okay because boron can get away with just 6. Remember, that's one of the unique things about boron. And there's 1, 2, 3 directions coming off of it. It means it looks trigonal planar, which means I drew it pretty close. It definitely should look like a Mercedes star, kind of like that. And you'll notice the dipoles are going to cancel once again because it's a symmetrical shape. And we keep going down the list doing that. I'm going to draw the last 2. Alright, so I finished drawing PBr5. It looks like this right here. I added up 40 valence electrons, spread them around the outside, go to the inside, there's nothing left. Remember, this is an expanded octet. It has more than 8 electrons around the phosphorus, but that's okay because phosphorus is in row 3 or below. It can have that expanded octet. But you'll notice that in this shape is a terrible drawing. If I were to draw it a little bit more accurately, remember there are 5 directions coming off of it, so it's the one that looks like trigonal bipyramidal, has head, feet, and then it has that belt line where the lone pairs go if we have any. But we don't have any lone pairs. This is the phosphorus in the middle, and you'll notice that it's very symmetrical. Everything pulls in opposite directions. So this one is also non-polar. So that's not the answer. We learned the other 2 aren't. So obviously D is going to be the answer. And the reason is because we've got it drawn right here. It had 20 valence electrons. It is definitely not linear. And the reason is because there are exactly 1, 2, 3, 4 directions coming off of it. It's tetrahedral, much in the same way that CH4 was. So if I were going to draw it a little bit better, I'd have my oxygen in the middle, right here. I would have a lone pair going up, a fluorine, another fluorine, and then that last spot would be for a lone pair. And you'll notice it's bent. There is a net dipole moment, and so therefore D turns out to be the answer. Alright, number 4. Why can a molecule with the structure of NBr5 not exist? And before we look through the answers, probably the best way to know is to draw out the Lewis structure. It becomes a lot more obvious. I counted up 40 valence electrons, and I put N in the middle, did the whole bromine thing. This is a lot like PBr5 that was on the previous question. And so it looks like it exists, but you'll remember that what's going on here is we've got an expanded octet. We have 2, 4, 6, 8, 10 electrons around nitrogen, and if we want to check and see if it can have 10, we look at nitrogen here, and you notice that nitrogen would max out at 8, and there are no d electrons close by for it to fill up more than 8. Phosphorus on the previous page could do that because it had these Ds down here that were very close in energy. So I think that's going to be the rationale. Let's see what the choices are. Nitrogen only has 2 energy levels and is thus unable to expand its octet. I kind of like this part, only has 2 energy levels. I think they're talking about the first energy level and the second energy level. So I think A looks pretty darn good. So we're going to circle it and just see what the others look like. B, bromine is much larger than nitrogen. Well, that's true, based on their location on the periodic table, and cannot be a terminal atom. Actually, terminal meaning can't be on the outside, like bromine is in this case, but that has nothing to do with size. It is impossible to complete the octets for all 6 atoms using only valence electrons. That's actually not true. We more than exceeded their octets. They all have 8 or more. And then D, nitrogen does not have a low enough electronegativity to be the central atom of this molecule. So what they're saying is really high electronegative atoms like fluorine are never in the middle. And that's actually true. Fluorine will never be a central atom. But nitrogen does have a fairly low electronegativity, and we see it in the middle all the time. So definitely A is the correct answer. Alright, so the next 2 I was trying to decide if I should leave in here, because you know that we're doing this review from the Princeton Review, the newest review book, and they have to do with gas laws, but you know that's what we're about to review next anyway, so let's look at them. An evacuated, that means there's no air in it originally. A rigid container, can't be changed its volume, is filled with exactly 2 grams of hydrogen, I'm assuming that's H2, and 4 grams of neon, and neon is not Ne2, it's not a diatomic gas. The temperature of the gases is held at 25 degrees and the pressure inside of the container is constant at 1 atmosphere. What is the mole fraction of neon in the container? So you remember that mole fraction, all we got to do is know the moles of neon and the total moles, and we can figure that out. So what I've started doing up here is I've started converting the hydrogen to moles and the neon to moles so that we could see what's going on. So we had 2 grams of hydrogen. We're dividing it by the molar mass, which is 2 grams per mole because it's H2, and I should probably label that it's H2. And so clearly that gives us 1 mole, and right away we're saying, look at that, AP does a wonderful job of making the numbers nice and easy. And then we get down to neon, and they do 4 grams divided by the molar mass, and I looked on my handy dandy periodic table, it came out to be about 20, and I'm thinking, you know, that's not too bad either. You know, 4 divided by 20 is about the same as, well, if I divide the top by 4, that's 4 divided by 4 is 1. If I divide the bottom by 4, 20 divided by 4 is 5, so it's 1/5, and so 1/5 we think is about 0.2 moles. Now, if you actually bought this Princeton Review, which remember is not a requirement, I noticed in their key, they said that 4 divided by 20 is a half. So clearly they have a mistake in their key. And that might make our next step a little bit more difficult because obviously they messed up the setup of it. But if we're going to figure out the mole fraction, which you remember the symbol for that is chi of neon, we're going to do the number of moles of neon, 0.2, divided by the total number of moles, which is 1.2. And so we've got to do 0.2 divided by 1.2. Well, the one thing I'm sure is it's not above half, so we can get rid of those 2. I don't even think it's a third, because a third of 1.2 would be like 0.4. If it was 0.4 divided by 1.2, that looks like about a third. So it looks like less than a third to me. I think A is going to be the correct answer. So it's not bad. That actually is a decent mathematic calculator problem, even though they seem to have messed it up in the book. And then number 6 here, what is the volume of the container? Well, so we might say to ourselves, we know a lot of the stuff in PivNert, and it might be possible to solve for the volume that way. We know the moles. Actually, we just found out that that was 1.2 moles in the previous problem, so go back and look at that. That's the total moles. We know R, it's 0.0821. The temperature they gave us, 25. We could convert it to 298. And we even know this is 1 atmosphere. And we might be able to weight our way through that and do some approximation. But the thing I think they're relying on here is this understanding that that if it's at STP, which is standard temperature and pressure, which it is here, it's at 1 atmosphere and 25 degrees Celsius, it is at STP, 1 mole is equal to 22.4 liters of gas. That's a definition. We don't use it much because we're rarely at STP, but we are here. So you notice we had more than a mole, so it's going to have to be greater than 22.4. So we can get rid of that, we can get rid of that, and then we get down to these two. And I don't think it's going to be 48.8 because that's double, actually it's more than double, 22.4. And we have a little bit more than a mole up here. We have 1.2. So I think C is going to be our best answer, and that's what the key says as well. By the way, for those of you who just busted out your calculator, you might have said, well, okay, if I do 22.4 times my 1.2 here, I don't get 33.5. But you remember, if you go back and look at the previous problem, they had a mistake in here. They think the number of moles is not 1.2, they think it's 1.5. So that's why it doesn't turn out to be exact.